Nitrogen and its compounds. Nitrogen was first discovered in 1772 by a Scottish physician and chemist, Daniel Rutherford. Free atmospheric nitrogen exists as a diatomic molecule. In chemical combinations, nitrogen is found as a mineral deposit in the form of sodium nitrate, ammonium sulfate, potassium nitrate, calcium nitrate, and many others. In living things, nitrogen is found in all proteins, nucleic acids, and some vitamins. It belongs to group 5 and period 2 of the periodic table with an electron configuration of 2 to 5. It is generally unreactive, which makes the atmosphere somewhat inert, slowing down the oxidation of matter. The approximate composition of air is 78.08% nitrogen, 20.95% oxygen, 0.93% argon, 0.04% carbon dioxide, and between 0 to 4% water vapor. Nitrogen, argon, and oxygen can be separated from air by liquefaction, followed by fractional distillation. Firstly, the air is filtered to remove dust. It is then cooled in stages to negative 200 degrees Celsius, at which temperature air is a liquid. As it is cooled, water vapor condenses and it is removed by absorbent filters. Carbon dioxide is then removed at negative 79 degrees Celsius when it freezes. The oxygen liquefies at negative 183 degrees Celsius. Argon at negative 186 degrees Celsius, and nitrogen at negative 196 degrees Celsius. The liquid nitrogen, oxygen, and argon are then separated by fractional distillation. First, as we said before, the air is cooled to negative 200 degrees Celsius and passed into the fractionating column. It is then gently warmed. The temperature rises from negative 200 degrees Celsius, and when it gets to minus 196 degrees Celsius, the nitrogen boils out and is collected. When it reaches negative 186 degrees Celsius, the argon boils out. And at negative 183 degrees Celsius, the oxygen boils out. In the laboratory, nitrogen is prepared by heating a solution containing equal amounts of ammonium chloride and sodium nitrite. In this experiment, sodium nitrite reacts with ammonium chloride to form ammonium nitrite. This is an example of a double decomposition reaction. Ammonium nitrite is unstable and decomposes on heating, giving out nitrogen gas. Ammonium nitrite is very unstable and decomposes even at room temperature. For this reason, it cannot be stored. This explains why it has to be prepared fresh by reacting sodium nitrite and ammonium chloride. If dry nitrogen gas is required, it should be passed through a U-tube containing beads wetted with concentrated sulfuric acid and then collected in a syringe. Nitrogen prepared in this method is pure and free of noble gases. It is less dense than the one prepared by the removal of oxygen and carbon dioxide from air. Physically, nitrogen is a colorless, odorless, and tasteless gas. It's slightly less dense than air. It's slightly soluble in water. It has a boiling point of negative 196 degrees Celsius. It doesn't burn nor support combustion. It's a neutral gas with no effect on litmus paper. Some of the important uses of nitrogen are creating an inert atmosphere for chemical processes, the Haber process for the manufacture of ammonia, gas chromatography, packing oxidizable foods such as ground coffee, and also liquid nitrogen can be used for the freeze drying of foods and preservation of tissue samples. Chemically, nitrogen gas is highly inert under ordinary conditions of temperature and pressure. The inertness is due to the presence of a triple covalent bond between the two nitrogen atoms, forming a nitrogen molecule. The bond is very strong and requires a lot of energy to break. Nitrogen does, however, react with some substances under certain conditions. In air, nitrogen and oxygen will combine when heated to a high temperature in the presence of a platinum catalyst to form nitrogen 2 oxide. This is a reversible reaction. The nitrogen 2 oxide is immediately oxidized further by more oxygen to nitrogen 4 oxide. Nitrogen 2 oxide is formed in the atmosphere during thunderstorms under the influence of heat produced by flashes of lightning. Nitrogen and hydrogen will combine when heated in the presence of an ion catalyst and high pressure to form ammonia. This reaction is used for the industrial manufacture of ammonia. Nitrogen will also react with highly reactive metals when heated to form metal nitrides. Examples of such metals are sodium, magnesium, and calcium. In particular, magnesium burns brilliantly in a jar of nitrogen to give magnesium nitride. The nitrides are easily hydrolyzed even by cold water, giving off ammonia and the metal hydroxide. Sulfur does not react with nitrogen even when heated. Oxides of nitrogen. Nitrogen forms the following common oxides. All these are gases at room temperature and pressure. Nitrogen 1 oxide. Nitrogen 1 oxide is commonly called dinitrogen oxide or nitrous oxide. It is prepared by gently heating ammonium nitrate. The reaction is exothermic and may become explosive if heated strongly. As a precaution, heating is discontinued after about 2/3 of the solid has decomposed. The gas is collected over warm water in which it is only slightly soluble. The gas can also be prepared by heating a mixture of any ammonium salt and a nitrate that will yield ammonium nitrate. For example, ammonium sulfate and potassium nitrate. The ammonium nitrate decomposes, giving off nitrogen 1 oxide. This method is safer with less likelihood of explosion as compared to the use of ammonium nitrate as the starting material. Physically, nitrogen 1 oxide is a colorless gas with a faint sweet smell. It is fairly soluble in cold water but less soluble in hot water, and this explains why it is collected over warm water. An aqueous solution of the gas is neutral to litmus. It is about 1.5 times denser than air. Chemically, burning metals, for example magnesium, and non-metals like sulfur and charcoal continue to burn in the gas, forming the corresponding oxide in nitrogen gas. Nitrogen 1 oxide itself does not support combustion. However, at high temperature of about 600 degrees Celsius, it decomposes to oxygen and nitrogen, and it is the oxygen so formed that supports the combustion of various substances. The reaction between burning elements and nitrogen 1 oxide are oxidation-reduction reactions. Nitrogen 1 oxide is in this case the oxidizing agent. When inhaled, nitrogen 1 oxide has a mild anesthetic effect. When mixed with oxygen, it is used as an anesthetic for minor surgical operations, especially in dental surgery. Patients recovering from nitrogen 1 oxide anesthesia may laugh hysterically. As a result, the gas is commonly called laughing gas. Next, nitrogen 2 oxide. Nitrogen 2 oxide is also called nitrogen monoxide or nitric oxide. It is usually prepared by the action of moderately concentrated nitric acid on copper tannins. Effervescence is observed as nitric acid reacts with the copper tannins, forming nitrogen 2 oxide. Physically, nitrogen 2 oxide is a colorless gas. It is only slightly soluble in water, forming a neutral solution. Its smell is unknown since on exposure to air, it combines instantly with oxygen, producing brown fumes of nitrogen 4 oxide. Chemically, nitrogen 2 oxide does not burn nor support combustion. However, it decomposes to nitrogen and oxygen at temperatures above 1000 degrees centigrade. The oxygen so formed will support the combustion of burning substances. Therefore, nitrogen 2 oxide will support the combustion of fiercely burning substances like magnesium and phosphorus, which produce heat over 1000 degrees Celsius. These are oxidized to their corresponding oxides, shown by the following equations. It will, however, extinguish a burning wooden splint and sulfur, both of which are not hot enough to cause its decomposition. Also, nitrogen 2 oxide oxidizes hot metals, for example copper and iron, to their oxides and is itself reduced to nitrogen. Again, nitrogen 2 oxide is instantly oxidized by atmospheric oxygen to nitrogen 4 oxide. An interesting reaction occurs between nitrogen 2 oxide and iron 2 sulfate solution. Nitrogen 2 oxide dissolves in cold iron 2 sulfate solution to give a dark brown solution of nitrous iron 2 sulfate. This reaction is used for detecting nitrogen 2 oxide. It is also the basis of the brown ring test for nitrates. If the nitrous iron 2 sulfate is heated, nitrogen 2 oxide is released. Next, nitrogen 4 oxide. Nitrogen 4 oxide is commonly called nitrogen dioxide. It is a poisonous substance and should therefore be prepared in a fume chamber or in the open. It is usually prepared by heating a nitrate of a moderately reactive heavy metal. Lead 2 nitrate crystals are the most suitable because, unlike most other nitrates, they do not contain water of crystallization, which would interfere with the preparation. Nitrogen 4 oxide is a dark brown gas. It has an irritating pungent smell. It is 1.5 times denser than air. It is easily liquefied on cooling, and it is highly soluble in water. Chemically, nitrogen 4 oxide reacts with water on dissolving to form a solution which contains nitric acid and nitrous acid. The solution turns a blue litmus paper red. If the solution is shaken vigorously with air, the nitrous acid is oxidized by oxygen to nitric acid. Nitrogen 4 oxide does not burn nor support combustion. However, it decomposes to nitrogen 2 oxide and oxygen at high temperatures. It extinguishes a glowing splint. This is because the temperature of the splint is not sufficient to decompose the gas. Vigorously burning substances like magnesium, phosphorus and sulfur will continue to burn in the gas, and this is because the temperatures produced are sufficiently high enough to decompose the nitrogen 4 oxide into nitrogen 2 oxide and oxygen. The nitrogen 2 oxide is decomposed further into nitrogen and oxygen. The burning substances are oxidized to their corresponding oxides, and nitrogen 4 oxide reduced to nitrogen. Nitrogen 4 oxide reacts with alkalis to form a mixture of a nitrate and a nitrite salt in equivalent amounts. For example, with sodium hydroxide, it forms a mixture of sodium nitrate and sodium nitrite. Next, ammonia. Ammonia, which is a gas at room temperature, is a compound of nitrogen and hydrogen. It is referred to as a hydride of nitrogen or a nitride of hydrogen. It is produced naturally by decaying nitrogenous organic materials such as proteins. Ammonia is prepared by heating a mixture of any ammonium salt and an alkali. The commonly used reagents are ammonium chloride and calcium hydroxide. On heating the mixture, ammonia gas is evolved. The gas is less dense than air and is therefore collected by upward delivery or downward displacement of air. It is highly soluble in water and cannot therefore be collected over water. Ammonia gas is dried by calcium oxide or quicklime. It cannot be dried using the usual drying agents, for example concentrated sulfuric acid or calcium chloride, because it reacts with them. With sulfuric acid, ammonium sulfate is formed. With calcium chloride, solid complex compounds such as tetraamine calcium chloride are formed. Physically, ammonia is a colorless gas with a characteristic choking smell. It is less dense than air and is easily liquefied under pressure. Ammonia is very soluble in water. It is demonstrated by the rapid rise of water in a jar of ammonia inverted in a trough of water, otherwise known as the fountain experiment. A fountain experiment is used to show the high solubility of ammonia in water. Phenolphthalein indicator is added to water in a beaker. Concentrated ammonia is added into a flask. This is warmed to release ammonia gas. The flask is corked and placed upside down, connected to the beaker via a narrow tube. Water rises up the tube and soon after reaching the flask, a fountain is seen and the water turns pink, indicating that the solution is basic. Low pressure in the flask sucks water up the tube. Because of its high solubility, a large volume of ammonia gas dissolves in the first few drops of water that arrives, further lowering the pressure and thus creates a large suction effect in the flask. This shows that ammonia is highly soluble in water. In fact, 1 volume of water dissolves 800 volumes of ammonia at 15 degrees Celsius. Chemically, ammonia turns a red litmus paper blue, showing that it is an alkaline gas. Ammonia does not burn in air, nor does it support combustion of burning substances. It extinguishes both glowing and burning wooden splints. However, it will burn in pure oxygen or in an atmosphere rich in oxygen with a greenish-yellow flame, forming nitrogen and water vapor. Catalytic oxidation of ammonia. In the presence of a catalyst, ammonia burns in oxygen, forming oxides of nitrogen. This can be demonstrated here. We use concentrated ammonia as the source of ammonia gas. A platinum wire is then heated and suspended in the flask containing ammonia. Ammonia and oxygen react on the platinum surface. Platinum catalyzes the oxidation of ammonia to nitrogen 2 oxide, which further reacts with oxygen to give nitrogen 4 oxide. The oxidation is exothermic and keeps the platinum red hot so that the reaction does not slow down. It continues glowing red hot until either ammonia or oxygen is depleted. Reactions of aqueous ammonia with metal ions. When ammonia dissolves in water, some molecules of ammonia react with water molecules to form ammonium and hydroxyl ions. The hydroxyl ions react with metal ions to form hydroxides. The hydroxides are insoluble in ammonia solution and form precipitates, some of which are white and others are colored. Some of the hydroxides, however, dissolve in excess ammonia, forming solutions, some of which are colored and others are colorless. These reactions are used in the identification of the cations.
We start with a solution containing calcium ions. We add a small amount of ammonium hydroxide. A white precipitate is formed. In excess ammonia solution, the white precipitate persists. Next is lead 2 ions. Add a small amount of ammonia solution. White precipitate is formed. Excess amount of ammonia solution. The white precipitate persists this time. Next is zinc ions. Small amount of ammonia solution. A white precipitate is formed. We add excess amount of ammonia solution and the white precipitate dissolves, forming a colorless solution. Then iron 2 ions. Small amount of ammonia solution. A green precipitate forms that persists even in excess ammonia solution. Next is iron 3 ions. When ammonia solution is added, a red-brown precipitate forms that persists even in excess ammonia solution. Finally, copper 2 ions. We add a small amount of ammonia solution and a light blue precipitate is formed. When we add excess ammonia solution, the precipitate dissolves to form a deep blue solution. And so in general, ammonium hydroxide or ammonia solution forms insoluble hydroxides with the ions of calcium, magnesium, zinc, copper, lead, iron and aluminium. However, the hydroxides of zinc and copper dissolve in excess ammonia solution due to formation of complex ions.
When exposed to air, concentrated hydrochloric acid releases hydrogen chloride gas. The gas reacts with ammonia, forming white fumes which consist of tiny solid particles of ammonium chloride. Industrial manufacture of ammonia, the Haber-Bosch process. Ammonia is produced on a large scale using the industrial implementation by Carl Bosch in 1913 and the laboratory scale ammonia synthesis developed by Fritz Haber. We've seen ammonia is a compound of nitrogen covalently bonded to 3 hydrogen atoms. An important precondition for ammonia synthesis is the efficient production of pure hydrogen. In several process steps, this precedes the actual ammonia synthesis. In the primary reformer, first, a natural gas methane is heated together with steam to about 800 degrees Celsius and is thereby converted into a mixture of carbon monoxide, carbon dioxide, and hydrogen. In the downstream secondary reformer, air is then added and the remaining methane gas is converted at above 1000 degrees Celsius by means of a catalyst and nitrogen is added. Since carbon monoxide and carbon dioxide will damage the ion catalysts used in ammonia synthesis, they have to be removed. Carbon monoxide is converted to carbon dioxide in a 2-stage process using special catalysts. The carbon dioxide can then be removed by a chemical scrubbing process. What remains is the pure synthesis gas consisting of 3 parts of hydrogen and 1 part of nitrogen, which can now be transferred to the actual ammonia reactor. To combine the 2 starting materials, nitrogen and hydrogen, to produce ammonia, the bonds in the diatomic molecules have to be broken. Under high pressure as well as temperature, nitrogen adsorbs onto an ion-based catalyst and is split up into atoms. Hydrogen can now be adsorbed and ammonia is produced. The catalyst itself remains unchanged. This reaction generates heat and therefore the reacting hot gases and ammonia reactor are cooled with the supply of a cold gas. This is achieved with a sophisticated flow system of synthesis gas based on the heat exchange principle. This way, the so-called equilibrium reaction can be prevented, in which the ammonia tends to decompose again into nitrogen and hydrogen. The ammonia is collected as a liquid and stored in tanks. The remaining synthesis gas is returned to the reactor and forms more ammonia. Next, nitric acid. Nitric acid is one of the common mineral acids. It is extremely corrosive and will attack almost all metals, rubber and coke. All apparatus used in its preparation and storage must be made of glass. In the laboratory, nitric acid is prepared by heating a mixture of equal parts of sodium or potassium nitrate and concentrated sulfuric acid. The nitric acid formed, being volatile, distills over. The concentrated nitric acid vapors are collected in a water-cooled receiver. The vapors are condensed into a liquid gradually. Pure nitric acid is colorless. However, the fumes appear brown due to the presence of nitrogen 4 oxide, which is produced by slight decomposition of nitric acid by heat. The nitrogen 4 oxide dissolves in the nitric acid, imparting a yellow color. Nitrogen 4 oxide can be removed by bubbling air through the acid. Nitric acid formed in this method is 98% pure and is called fuming nitric acid. On a large scale, nitric acid is manufactured by the catalytic oxidation of ammonia in the Ostwald process. A mixture of pure dry ammonia gas and dry dust-free air in the ratio of 1 to 10 is fed into the catalyst chamber. In the presence of the platinum gauge at temperatures of 700 to 800 degrees Celsius, the ammonia is oxidized to nitrogen monoxide or nitric oxide. This is an exothermic reaction. This nitric oxide gas is then allowed to pass through the cooling tower and the gas is cooled to 50 degrees Celsius. This chamber has an inlet for fresh oxygen. Here, nitric oxide combines with oxygen to form nitrogen dioxide. This nitrogen dioxide and non-reacted oxygen then flow into the absorption tower, which is a stainless steel tower packed with acid-resistant quartz. Water is sprinkled from the top. The water dissolves nitrogen dioxide and non-reacted oxygen to form a solution which contains nitric acid and nitrous acid. The nitrous acid is oxidized by oxygen to nitric acid. Nitric acid obtained by this process contains 65% acid and 35% water. Its concentration can be raised further by fractional distillation. It is stored in dark bottles because it slowly decomposes on exposure to light at room temperature and pressure. Chemically, concentrated nitric acid decomposes slowly at room temperature, particularly in sunlight, and rapidly when heated, giving off nitrogen 4 oxide and oxygen. Nitric acid reacts chemically in two ways: one, as a strong acid, and as a strong oxidizing agent. Acid properties of dilute nitric acid. Nitric acid is a strong acid which is almost completely dissociated into ions in dilute solutions. It neutralizes alkalis, forming a salt and water only. For example, with sodium hydroxide, sodium nitrate and water are formed. Dilute nitric acid reacts with insoluble bases to form the corresponding nitrate and water only. For example, with copper 2 oxide, it forms copper 2 nitrate and water. Dilute nitric acid reacts with carbonates and hydrogen carbonates, producing carbon 4 oxide. With sodium carbonate and sodium hydrogen carbonate, sodium nitrate, carbon dioxide and water are formed. Nitric acid reacts with all metals except gold and platinum. Unlike other dilute mineral acids, which react with the active metals to give a salt and hydrogen gas only, nitric acid only gives hydrogen and a salt when the very dilute acid reacts with magnesium or calcium. The products formed with other metals depend on the concentration of the acid and the temperature. For example, with cold, moderately concentrated nitric acid and copper, nitrogen 2 oxide is formed. Concentrated nitric acid acts as a powerful oxidizing agent. It does this by acting as an acceptor of electrons. For example, concentrated nitric acid reacts with copper, forming brown fumes of nitrogen 4 oxide, copper 2 nitrate, and water. In this case, metallic copper loses 2 electrons, being oxidized to copper 2 ions, which go into solution. The electrons are accepted by nitric acid, which is reduced to nitrogen 4 oxide. Iron and aluminium react with concentrated nitric acid, forming a protective layer of oxide which prevents further reactions. Concentrated nitric acid reacts with acidified iron 2 sulfate, forming nitrogen 2 oxide gas. The green iron 2 sulfate solution changes color to brown. This is due to oxidation of iron 2 ion to iron 3 ion. Colorless nitrogen 2 oxide is immediately oxidized by atmospheric oxygen to nitrogen 4 oxide, which is a brown gas. Again, concentrated nitric acid reacts with sulfur, forming nitrogen 4 oxide gas and sulfuric acid. Finally, concentrated nitric acid reacts with charcoal, forming brown nitrogen 4 oxide gas and carbon dioxide gas, which forms a white precipitate with lime water.